I'm going to talk about something quite different than what has come before. I'm a chemist, and I'm going to try not to talk about too much chemistry. I've been asked to keep this as a broad overview. So if I drift into too much chemistry, shout at me, Didier. Our perspective is slightly different. So our perspective is to try and join that gap, join the gap between the planetary science we've been hearing about and biology and biochemical reactions, and really to try and understand this process of how the planet that we know now came to have life as we know it now on it, and whether the trajectory from kind of the astronomy through to the planetary science that we've already heard about impacted that process, and whether we can still see evidence for the chemistry that led through those reactions into life in modern organisms today. This is a really old question. So here's from Charles Darwin, basically highlighting the same question that we want to address many, many years ago. It is no better, I think, addressed now than it was then. There's so many things that we don't understand, but we can basically formulate the same question now that Charles Darwin thought. How do we get from simple chemical species to a protein molecule, a molecule of life that's ready to undergo evolution, so that something that can become life? So we've already seen this plot before. And I don't put this up to reflect on the geology going on here, because I'm not a geologist, but just to think about how profound this transition is from an abiotic system to a biotic system, and how much amazing science is encapsulated within that process. And for me, that is why this is the topic that we should address as scientists. The biggest question that I can think of in science, and therefore it's the question that deserves my attention. So we actually haven't seen this yet. A lot of what we've seen is focused on forming planets back here. But I put this up to put in perspective how long ago what we're talking about is. So this is a timeline of life's history, really focusing on life on our planet in billions of years. And here we are. And the whole of human existence, our existence as a species, is gone in the blink of an eye on this time frame. For perspective, look, here's the dinosaurs. Look how close we are to the dinosaurs in the perspective of Earth history. But we can track life back through the geological record all the way back to about 3.8 billion years ago. And it's questions that are in this gap, in this time gap here between the formation, perhaps of the moon, and the colossal events of the early Earth's history. It's cooling to the point where organic molecules can form on the Earth, to a time when we have life. What fills this gap? What chemistry happens here? How does this deliver life? And the sad thing about this trajectory is the further back we go, the more interesting the questions get, but the less and less record we have. So it's literally eroded over time as we move back through this plot. And this makes it very difficult to constrain how life started and what happened at that time frame in the geological record. There is another record of life's history. It carries this record itself. So all organisms inherit information from their parent organism, and we can use this to plot family trees. Is one that's got familiar organisms on. And by cross-referencing these organisms, we can learn about their common origins, and this can push us back and learn about the history of life. But sadly, this has a point beyond which it cannot go. So the information we're cross-referencing is in living organisms. And we can only cross-reference the organisms that are currently alive, and this allows us to only push back to a certain point. And this lets us push back as far as the last common ancestor of all organisms that are currently on the Earth, what we would call Luca. But Luca, as our last common ancestor with everything else that's on Earth, is a very long way from the origin of life. If we think about Luca in the context of life, then an appropriate model perhaps for how complicated Luca is in the terms of aeroplane evolution. So in terms of aeroplane evolution, Luca is a really sophisticated cell. It's basically a Boeing 747. Whereas what we're trying to think about is, how did life first start? So what is the living model for the Wright brothers aeroplane? And this puts us in a bit of a conundrum from a chemical perspective, that we have two really great sources of information about life and life's history, but both run out. Both run out before the point when we can make predictive assumptions about how life began. And this means that we can't, in those historic records, discover the origin of life. So instead, we have to, as chemists, invent it. So where the historic records run out, organic chemistry knows no bounds. We can change the molecules, we can make predictions, we can design, we can test, we can generate our own data to try and model how an organism first began. So we can do this by, rather than trying to find life, by trying to build life. So if we look at life in a very broad brushstroke sense, in a very top-down perspective of what it is, we have a cell that is bounded by a membrane that defines inside and outside. It has to carry some form of information that can be passed to the next generation. We call this its genome. Inside the cell, there's going to be something that carries energy to keep the cell out of equilibrium, and there's going to be some form of catalysis that differentiates inside and outside. So different reactions occur within the cell than in the general environment. So there are so many different types of chemistry here that I can't cover them all, and all are interesting and all should be explored. What I'm going to do instead is give you a little tiny bit of chemistry. I'm going to force some chemistry on you. And I'm going to focus on the molecules that build the biggest component of the cell, proteins. So protein molecules, here's a protein, are built from simple precursors, small molecules. So here, amino acids that are strung together into peptides that are then built into protein molecules, which is kind of the catalytic workhorses, the structural bulk of our cell. So we might think that if we look at these molecules, this would be predictive about the type of chemistry that would lead to their formation. So in our cell, all organisms have 20 different amino acids that are universally coded to form proteins. And they all have this generic structure where we have an amine, an acid, and one of 20 side chain residues. And to build these compounds into proteins, we have to make this green bond, the peptide bond, and to do this, we have to take water out of this. So we might expect, given the fact that this is a universal structure of life, this compound would be predisposed to form peptides in water, but it is not. It is not because this molecule forms a salt in water. So under physiological conditions, the acid we have to ligate and the amine we have to ligate are both blocked by salt formation. And this is a physical property of these molecules. So these molecules, we need this free amine, but we don't have this free amine at physiological pH. We have to go to highly alkaline conditions before we start to get the amine we have to couple to react. So this seems problematic if we have to operate at neutral pH. But so we can ask questions as a chemist about this system, not just assume that we have amino acids. So why are we using amino acids to build peptides? We assume this because this is what we're taught. We're taught at school, university, and textbooks that peptides are made from amino acids. But why? Where do these molecules actually come from in the context of the early Earth? So if we're going to build these molecules, if we're going to get these molecules now, we're going to extract them from life. The biosphere is replete with amino acids. They're the bulk of what's in cells. But if we're going to build these types of molecules from these types of molecules that were introduced in the previous two talks, then we have to ask, how is this going to happen? What's that mechanism, and what does that mechanism tell us about how life might have started and the chemistry that will underpin that? So we take some of these simple molecules, simple diatomics, so hydrogen cyanide and sulfide can be brought together to make these molecules, which are almost amino acids. They're aminonitriles. Okay, so the difference between our amino acid and our aminonitrile is one, we can form this very easily through abiotic processes, and two, this carbon here is, rather than attached to two oxygens, attached to one nitrogen. So this appears to be the most robust, the simplest abiotic mechanism to make amino acids, that we make aminonitriles and hydrolyze them. But then we have to ask, what do those aminonitriles tell us about potentially the origin of life? And the properties of those molecules are totally different. So if you look now at the pKa of the amine, so this is how basic it is, how likely it is to be protonated, it is 4 orders of magnitude less basic, 4 orders of magnitude less likely to be protonated on this nitrogen. So it's going to be nucleophilic in the physiological range of pH. This means it's reactive in water. We can take this amine, it can now be acylated, we can start to build peptide bonds with it. And as we acylate this molecule, it then activates the nitrile to addition of hydrogen sulfide. This lets us turn the nitrile into a thioacid, and we can then close a ligation cycle to build peptide molecules in water controlled by these prebiotically plausible molecules that we'd expect early geochemistry to be able to deliver us. So finally here, in the context of these molecules and reflecting on the structures of life and what they can tell us, this is one of our 20 amino acids. This is lysine, and it's an interesting test case because it's got 2 amines. So there's an alpha amine that has to be ligated into a peptide bond, and it has this side chain amine that's sort of a functional part of the molecule, but shouldn't be ligated into the amide backbone. And if we try and ligate an amino acid in water, well, we have to lift the pH a little bit so that these become reactive. And we have 2 amines that are basically equally reactive and equally likely to be coupled into protein molecules. So if we take the amino acids that we expect based on what we're taught that should be coupled into protein molecules, we're going to get a complex mixture of both of these nitrogens attached into protein's backbone. But if we take the aminonitrile, now the alpha amine and the side chain epsilon amine, these have 5 orders of magnitude different basicity. So at neutral pH, the side chain is completely quenched by protonation, whereas the alpha amine is deprotonated and nucleophilic, so can be selectively coupled into the peptide backbone. Okay, so I'm going to end there, and there's so much more chemistry that can be discussed, and hopefully this gives you a flavor about how we can think about chemical mechanism, how that chemical mechanism can be interpreted based on the types of molecules that can be presented to us in a geological context, and how if we keep working at this, if we keep thinking about the context of all these different molecules in the context of the early Earth and other planets beyond the Earth, we can realistically develop a model to get from planet to life and understand how and where that process will happen across perhaps the whole universe. So I'll end there and thank everyone for listening.
So you showed a pathway, like a cyclical pathway. Is that something that had to happen once and then life just continued along via its more current pathways, or is it something that continued for an extended period of time and then at some point later we co-opted a different method of producing these?
If you want to build a protein molecule, which I don't necessarily think you have to make anything as large or complicated as a protein, you'd have to do this thousands of times just to make one of those molecules. So to make any peptide, so to make a dipeptide, you do this once. To make a tripeptide, you do it twice, etc. I think, in the context of how we get from here to here to here, this in some ways is the materials that are available to us. So as I already alluded to, the chemistry of life has changed remarkably, even in much more recent times. And by that, I mean 2.5 billion years ago, we heard about the Great Oxidation Event. So this is when the Earth went from a period of having low oxygen to high oxygen. That fundamentally changed the way that biochemistry works. Okay, we couldn't exist without that transition having happened. The chemistry of our biochemistry couldn't be the way it is without that transition. And I think we have to bear in mind that life is not fixed. So the chemistry that operates now in biochemistry is a reflection of the materials that biochemistry has available to it. And as those materials have changed throughout the whole course of evolution and the history of the Earth, those reactions will change. So early in Earth's history, where molecules like hydrogen cyanide could be highly available through geochemical processes, then those are the molecules that will define how a cell is built. Because a cell then has hereditary kind of memory, once you build into that process something that is defined by the chemical reactions that initiate that process, there's inertia to get away from that. So then you take that process you already have and you learn to build metabolism that recovers and recoups the molecules that you need, that you've learned through evolution that are required to keep your cell alive. So I think over the course of biological history, metabolism will change. The actual reactions that biology uses will change, and these reactions will over that course change, transmute, and become the reactions we know now to recycle amino acids, to bring amino acids back in that are consumed from the environment, to deliver the same reactions controlled enzymatically rather than chemically.